eddy separate the flows. And towards the end of this, there'll also be a travel log of all his travels that he's done during his PhD all over the world. So, fairly lively.
So you can't leave early.
Yeah, as I said earlier on, Leanne Webb has kindly gone through the talk and got rid of all the equations on most of them. So it shouldn't be too difficult to follow, hopefully. Vasily has just completed his PhD at Melbourne University and also had co-supervised at Monash and also at the University of Poitiers, which is French. So he's got a double badged PhD, whatever that means, which means that it's basically recognised both by Australian and by French universities. His supervisors were Andrew Wu at Melbourne and Julio Soria at Monash, and his topic of his PhD was aerodynamic control theory, which is basically flow of airfoils and turbulent flows at various Reynolds number. There are some quite interesting similarities about the approach he's taking to the sort of approaches we use in atmospheric science. In particular, flow over an aerofoil, although the fluid dynamical equation is slightly different, is quite similar to flow topography, both in terms of Lee wave generation and also in terms of Rossby wave generations. And the methods he's going to use to actually look at these problems are also very similar to the methods we use in atmospheric science, which is basically empirical orthogonal function decomposition and representation of the flow, the downstream flow, in terms of empirical orthogonal functions. Vasily joined us here at CSIRO in January this year, and he's currently working on parametrization of subgrid turbulence for climate models in the atmosphere and ocean. So without further ado, I'll
cheers. Thanks, Jorgen. All right, thanks for the intro. So I guess we'll just get started. So I guess it's the first time we're giving a talk here, so I thought I'd start off with why I'm actually here. Jorgen touched on this before. So I'm working with Jorgen on developing turbulence models for large eddy simulation. So I apologise to the people that are full bottle and all this stuff, but for those of you that don't know what large eddy simulation is, the large eddies are essentially resolved by a computational grid, and the eddies that are smaller than the smallest cell are modelled. In the current approach, the subgrid model coefficients are determined from a reference high resolution data set, but I'm looking to develop some universal scaling laws so that we don't need this reference data set. But that's a talk for another day. Today I'll be presenting my PhD work on aerodynamic control. Thought this would be a good opportunity to illustrate the similarities between the two fields and also to demonstrate a technological solution to reducing energy consumption and also increasing energy generation. So this is some motivation of my PhD project. The performance of many engineering systems relies on fluid flows remaining attached to aerodynamic surfaces. The particular flow configuration of interest for today is an airfoil, so for example an aircraft wing or a wind turbine blade. So the performance of these systems can be improved via aerodynamic control. And the control scheme I'm going to illustrate today requires a simplified model of the flow that captures all the pertinent physics. And this simplified model consists of fluid mechanical modes. So the aim of this project is to draw out these fluid mechanical modes. Okay, so this is an experimental open loop control study. So it's open loop in that it's forced at a particular frequency and the performance isn't measured at all, so there's no loop going on here. So on the left here we've got our airfoil, that particular angle of attack. So that's the angle of the airfoil with the free stream velocity that's coming in from this direction. So at this particular angle and Reynolds number, or speed, the flow separates from the leading edge. So that means you get zero lift. So if this was a plane, it'd be falling out of the sky. So it's obviously you want to avoid this sort of situation. But at this particular angle and Reynolds number, if we force the flow at the leading edge at the correct frequency, then we reattach the flow. So this is analogous to forcing a system at its natural frequency. So, and this, the best frequencies was determined experimentally by trial and error. So in that way, it's an open loop approach because we force it and we see what happens. There's no sort of loop going on here. So open loop studies are good because they can illustrate the physics, but their closed loop approaches can improve even better, even improve performance. So this is what a proposed closed loop system would look like. So this is our plant or our physical system. So the plant, that's a controlled terminology. So this is the physical system, and we would observe this physical system with a partial measurement. So typically you can't measure everything. So what we may be able to do is to measure pressure on the surface of the airfoil. But this partial measurement is perhaps not enough information to control the flow. So what happens, this partial measurement gets sent to an estimator, and this estimator estimates or guesses what the flow structures would be around the airfoil. And it's for this particular component that we need our fluid mechanical modes. I think this, correct me if I'm wrong, but this is perhaps similar to dynamical downscaling, or where you have an observation and you're forcing your model to approach that observation. So I think it's analogous to that, but you guys can correct me later. So now that we have an estimate of what's going on, this state estimate is sent to a controller, and then the controller figures out what the best forcing frequency is, and this control force is applied numerically to the estimator to test if it actually is a good frequency or not, and then physically to the physical system via actuators. So this could be done in real time. That's the...
POD modes are EOFs.
Yeah.
In our terminology, Temporal orthogonal functions.
Yeah, I'll get to that in a sec. So when I first started, I wanted to do all of this, and then I quickly realized that that was not going to be possible in 4 years. So my PhD focused on the uncontrolled state, so characterizing what's going on there, what are the pertinent physics, and then determining which modes would best describe the unsteady scales of motion, and also how that flow would respond to a applied control force. So the POD modes, or the EOF modes, or whatever you want to call them, they're the most efficient way in summarizing the unsteady scales of motion. So it's a way of compressing the data. So instead of having gigabytes upon gigabytes of data, you can compress them into a couple of modes. And the linear stability eigenmodes, these represent the natural frequencies of the system. Okay, so I'm not going to talk about the eigenmodes today because it's very mathsy, and and the other two components are a bit more visual, so I thought it'd be a bit easier to be able to convey the message. Okay, so today I've got two solid research questions I'm going to discuss. The first is what are the flow characteristics of the uncontrolled state? So to answer this, I'm going to numerically simulate the flow and characterize the flow field. And second, how to most efficiently represent unsteady scales of motion. And as we touched upon, I'm going to use a proper orthogonal decomposition to represent the fluctuating scales of motion. And as Jorgen said before, proper orthogonal decomposition is the same as empirical orthogonal functions, which is the same as principal component analysis modes, which is the same as single value decomposition. They're all just the same name for the same, different names for the same thing, depending on which field you come from. Okay, so I'm going to use this sort of picture here as like a contents page, I guess. Every time you see this, I'm coming up against something new. So I might just pause here for questions if anybody's not clear with anything I've already said before I move on to the next part.
Well, in reality, that control force, what
Yeah.
would that be?
It's a jet, so I probably didn't explain that properly. So this little part here it would be a cavity that sucks the working fluid or the air in and then spits it back out again. So it's called a zero net mass flux jet, and that just means that there's no mass added to the system because whatever you suck in, you spit out again, but you're adding momentum. So typically, the velocity or the additional momentum you add in is negligible compared to the momentum of the aircraft. So you're really trying to hit the natural frequency of the system and allow the properties of the fluid to do the work for you. Anything else before I move on? No? Okay. So feel free to jump in any time. Okay, well, so now I'm going to characterize this flow state before we start producing modes from it. So I thought I'd start with characterizing our current understanding of these types of flows. So this is how the flow changes with angle of attack or with angle of airfoil. So this is at no angle. So if this is an aircraft, it would be cruising at altitude. So here we have wake structures. So you would expect one dominant frequency of the wake shedding. As the angle increases slightly, we still have the wake frequency, but the flow would separate at the leading edge and reattach at some point downstream. And there's a frequency associated with the beating of this bubble, separation bubble. And if the Reynolds number is large enough, we also have a Kelvin-Helmholtz instability or a shear layer instability at the leading edge there as well. And as the angle increases even more, this separation bubble is no longer there because it doesn't reattach. So all we have now is the wake frequency and a shear layer instability at the leading edge. And it's this last case that is representative of the flow I'm going to discuss today. Okay. Yeah, sure.
Why do you say the first one doesn't have separation? It's got little turbulent things.
That's associated with the shedding, the bluff body shedding in the wake. Separation means the velocity profiles here would be going in the opposite direction. That's what separation means.
So if you have the eddy over the wing, that's immediately a separation.
Yeah, that's right. So here, no, that's fine. We would have streamlines that would stick to the flow, and then they would sort of separate just before the end, and where you would get shedding. But so here separation is clear, and here separation just goes straight off. Yeah. Okay. Next one. Okay, so what I showed previously was how the flow changes with angle. So this gives you an illustration of how the flow changes with speed or with Reynolds number more strictly. So in the first case here, this is a Reynolds number of 200. So this Reynolds number, it's steady, nothing's moving, very boring. It's coloured by vorticity. So the red is positive vorticity. So it just essentially a measure of curvature. So red means that the flow is curving in this direction, and blue means the flow is curving in that direction. And at Reynolds number 300, so as the speed of the airfoil increases, the flow becomes unsteady, but still two-dimensional. So this flow is sort of extruded out of the page, but it has a two-dimensional shedding pattern. And at Reynolds number 800, the flow becomes three-dimensional. So the green structures, they're the two-dimensional sort of rollers that are doing qualitatively the same thing than what's going on up here. But now we have these streamwise-oriented 3D red and blue structures. So that's illustrating that the flow is now three-dimensional in nature. So now when we increase the Reynolds number again, and this is the target Reynolds number, you can see that it's far more complicated. So as we've seen in the previous two cases, there is this sort of two-dimensional inherent nature to these flows. And it is also present here, but we just can't see it because of all the fine-scale turbulence that's masking it. But I'll illustrate a way of how to illustrate the bluff body shedding later on in the talk. So this is the case that we're primarily interested in. Okay, so for those of you who are familiar with numerical simulation, here are some details. For those of you that aren't, it doesn't matter. It's not important for the talk. To generate all the data that you previously saw, I use an unstructured collocated LES code developed at Stanford Center for Turbulence Research. It discretely solves the Navier-Stokes equations in time and space. And I'm using the dynamic Smagorinsky model for the subgrid scales. It's the model of Germano. Okay, okay, here we go. So here's some details of the grid. So this is the airfoil that we've all seen before, and it's put in a computational domain of this size. And the computational domain is discretized into a whole bunch of grid points. So this is in the vicinity of the airfoil. So it's very fine, but it's still actually not fine enough to resolve all of the scales of motion, which is why we're using like LES. So this grid is extruded in the Z direction, so it's extruded out to the page. There's 128 cells in that direction as well. We have a Dirichlet boundary condition, so I'm applying a velocity of U infinite, or the free stream velocity, along this boundary. And on this boundary, I'm applying a Neumann boundary condition. I'm just saying the velocity is not changing over that boundary. And I'm saying the velocity there is 0. Okay, in terms of the solution procedure, the simulation is marched forward in time with a constant Courant number until initial transient response is removed. And then from that point onwards, I'm using a constant time step until all the statistical measures are stationary. Again, if that doesn't mean anything to you, it doesn't matter. So I also undertook multiple simulations at different resolutions, and the statistical quantities all agreed with each other. And also probed so I have time histories at these 3 locations. This is the important ones. This is in the shear layer, which I'll discuss in some following slides. But I'll now show how the statistical quantities agree with experiment along these 4 profiles, A1 to A4. So A1 is just downstream of the leading edge, or just near the front, and A4 is at the back. Okay, so these are profiles of average tangential velocity. So this is the velocity tangential to the surface. The circles are experimental measurements from the water tunnel experiments from the very beginning. These are PIV measurements, or particle image velocimetry. And the size of the circles are proportional to the error in the experimental measurement. So along each of these profiles, the mean tangential velocity agrees quite well, I think, with the experiment, as does the mean wall normal velocity. So this is the velocity normal to the airfoil surface. So these are the means, and these are the RMSs, or the square root of the variance, and they also agree quite well. So that's RMS of the tangential velocity, and RMS of the wall normal. So now that we have some, I guess, some confidence in the results of at least the statistical quantities, I'm going to illustrate some of the instantaneous flow structures so we can sort of understand how this flow behaves. So previously when I showed that movie and we couldn't see any of the large scale 2D structures because of the fine scale turbulence, I'm using somewhat of a hand wavy means of illustrating the large-scale structures using slices of pressure. So what I'm looking for here are pressure minimums that are under swirl or under rotation. So I guess it's sort of like a cyclone, pressure minimum with under rotation. So this is the flow at 4 different instances in time, and I've purposely shown them to illustrate that the flow is periodic over this time frame. So I've identified 3 large-scale structures here, and from one time step to the next, they get convected further downstream again, and then subsequent snapshot has the similar properties to what we see here. So we can say that this bluff body shedding mode, or this sort of 2D wake structures, have a period of about 1.6 non-dimensional seconds, which means that it has a frequency of about 0.625. Now, I'll do this more concretely later, but this is just to illustrate the sort of structures we're talking about. You may also notice these small-scale structures at the leading edge. They're slices of the shear layer instability, and we'll now look at that in a bit more detail. So now this is a bird's eye view, or a plan view of what we saw before, and now I'm focusing only at the leading edge here. So I've identified, these are isosurfaces of Q. For those of you that don't know what it means, it doesn't matter. It's just a definition of a vortex. So we're looking at the boundaries of these vortices. So at the leading edge, we've got these structures S1 and S2, these sort of tubular type structures. And from one time step to the next, these structures get convected further and further downstream. And we see a new one, S3, that's beginning to form here. And at the following instant, S3 is in the same position as S2. So this particular mode has a period of about 0.08, which is actually 1/20th of the wake structures. So this is a much faster moving mode. So this frequency is much larger, it's about 12.5. You may also notice at a certain point these tubular structures begin to get kinks in them. So from one period to the next, these kinks get offset, so and produce a sort of a macro structure. So this macro structure needs two of these tubes to go past. So the period of this sort of grouping of kinks, or hairpins, as we call them, happens at twice the period of these shear layer tubes. So it would have half the frequency, or it's subharmonic. So this will make more sense in the next slide. So now what I did, I took that leading edge probe, that L probe right at the leading edge in the shear layer, and I took a Fourier transform of that data, and so it just essentially breaks the signal up in a whole bunch of sine curves and determines the energy associated with each of those frequencies. So this is plot on a log linear graph, and we need to plot the energy times frequency to ensure that the area under this curve is equal to the variance of the signal. It's just a way of clearly illustrating the peaks. So here we've identified the wake frequency. So we've got a little peak here at 0.625, and previously when I illustrated those slices of pressure, we sort of estimated that the wake structure would have about that frequency. And we've also identified the shear layer frequency, at a frequency of about 12, and it's subharmonic. So this peak here is associated with the grouping of those hairpins. Okay, so now that's pretty much this flow state characterized. So before I move on to generating modes associated with this flow state, let's pause for questions again. If anyone has got anything? No? Keep going? Okay. So now what I'm going to do, before I delve into generating these EOFs for the highest Reynolds number case, I thought I'd introduce the approach on the lower Reynolds number cases that I previously showed. So first on the steady two-dimensional flow, then the 3D flow, and then the target turbulent case. So just to give a brief overview of what a proper orthogonal decomposition is, it decomposes a series of snapshots or observations into orthogonal modes. This is introduced to studies of turbulence by Lumley. And we can reconstruct the flow using a certain number of modes, n modes, like this. So u, that's the velocity as a function of space and time. So this is instantaneous at a given instant. And this is the time averaged velocity. So it's not a function of time. So it's the average over all of the observations. And this component here, this is the fluctuating part, or the unsteady part. So, and it's this unsteady part that we decompose into a series of orthogonal temporal modes and spatial modes. It's a statistical approach, so it's important that we apply this over an integer number of the fundamental time period. Again, this will make some sense when you see all the examples. Okay, so we're applying this to the steady, the unsteady two-dimensional flow at Reynolds number 300. I generated this data using the same code as previously. And now I probe the flow again at these three locations, L, B, and T. I took the velocity signal, did a Fourier transform, and we find that all of those three locations have a distinct peak at 0.49. So this means that the shedding period is 1 over the frequency, so it's about 2 non-dimensional seconds. So now I'm going to generate these decompositions over this time period. So this is the proper orthogonal decomposition. So it was undertaken over the period T wake. And this funny looking spectra here, this is the energy associated with each of the modes that we've identified. So the first two modes have roughly the same amount of energy. The next two modes have the next same amount of energy. So I guess the difference between a proper orthogonal decomposition and say a Fourier decomposition. A Fourier decomposition, as we saw here, would have peaks at certain frequencies, depending on the data. But a POD or EOF or whatever is constructed so that by definition, the first mode or the first the first mode has the most amount of energy and it decays monotonically to the last mode, which has the least amount. So that's the sort of fundamental difference between the two. Okay, so the first two modes are the same amount of energy, and the temporal modes are scaled proportional to their energy. So this is these are the temporal modes here. So because we constructed the POD over 2 non-dimensional seconds, so all of the temporal modes are about 2 seconds long, and mode 1 looks like a sine curve sort of thing, and mode 2 also looks like a sine curve, same amplitude, but it's temporally shifted out of phase. So this is a classical properties of these sort of modes. So modes 3 and 4 down here have the same energy as each other, and they're also temporally shifted out of phase from each other. But you may not notice that they also have twice the frequency. The dominant frequency is twice that of the previous modes. And you can see that modes 3 and 4 have a lot less energy than modes 1 and 2. So in modes 1 and 2 capture 94% of all the fluctuation energy.
No, so the modes 1 and 2, or the modes 3 and 4, they're sort of the same mode as spatial, is that right?
I'll show you the spatial properties on the next slide. Maybe that'll clear things up. Yeah.
One of the interesting things about this result compared with our results in our field is that you get a much better matching of pairs because the EOF really represent a real dynamical mode. Yes. I mean, our eigenmode, which is a propagating structure. And so, but in our case, when we look at them, we quite often get matching pairs. Quite often the frequencies are not quite as good as they are here. Right? They're very closely related in this.
Yeah. So these are the spatial. This is the spatial POD mode. So this is the first one. So you can see we have these large structures in the wake, and mode 2 is a spatial shift of mode 1. So you see that little black dot shifted. So these two modes, if you can imagine adding these two guys together, you will be able to reconstruct that sort of nice shedding pattern that we saw in the movie. And modes 3 and 4, the size of these structures is roughly half of the dominant structures in modes 1 and 2, and they're also spatial shift of each other as well. So using these two, you can reconstruct 94% of the energy, and these two just sort of fill in the gaps, essentially. Okay, so now that's the simplest case. Now we're going to move on to the unsteady three-dimensional flow. So this is, again, 4 snapshots of the Reynolds number 800 case at different instances in time. So if the again, isosurfaces of Q and coloured by rotation in about the x direction. So green means it's not spinning about this direction. So it just means that it's sort of, these green structures are spinning this way, but they're not spinning this way. That's what that's saying. And the red are spinning this way, and the blue are spinning that way. Okay. So if we look at this first part here, in the next time step, this green structure is separated from the structural lineage, and then it propagates downstream and downstream again, and the next snapshot sort of looks the same as the first one. So this bluff body shedding mode has a period of about 1.6, but you may notice that from one bluff body shedding cycle to the next, the spin of these 3D structures changes. So this one here was red in the previous cycle, where the one before that it was blue. So these 3D structures actually periodic over twice the bluff body shedding cycle. Okay, so that'll become important when we look at the POD modes. So now I've constructed PODs over 8 bluff body shedding cycles. I might also point out the results for the 2D data I showed before were constructed over 1 cycle, and then I did it again over 2 cycles, and the results were identical. So that's a way of showing convergence of your spectra. So here the flow's a lot more complicated, so you need a lot more data to illustrate convergence. So I did two decompositions, one using 8 bluff body shedding cycles and another using 16. And the energies are both plotted on this graph. So you can see the first 4 modes have got the same energy, irrespective of the number of cycles you've used. But past that, the energies tend to differ. So we can only really say that the first 4 modes are converged. After that, we need more data to illustrate convergence. So there was 17.5 gig of data for the 16 cycle case. So I needed to develop some parallel approach of doing this. And in this case, the first 2 modes contain 65% of the energy. But in the previous, more simple case, the first 2 modes contain 94%. So as the flow becomes more complicated, you need more modes to summarize what's going on. So now these are the first 2 modes, modes 1 and 2. These are the temporal modes. So you see mode 1 is a temporal offset from mode 2, and the dominant frequency is that of the bluff body shedding. And here, these are the spatial modes. And mode 2 is a spatial shift of mode 1. And then when we go to modes 3 and 4, you'll see that modes 3, the amplitude of modes 3 and 4 is less than mode 1 and 2. So if I flip back. So that's, again, illustrating that there's less energy in these modes. But also, the dominant period of modes 3 and 4 is double that of mode 1 and 2. So you'll see that so the frequency is half, which is sort of what we saw previously with instantaneous snapshots, how this 3D mode takes twice as long. And it's obvious from the spatial modes that these are obviously 3-dimensional in nature, and one is a spatial shift of the other. Okay, so now we're going to illustrate the POD spectra of the target case. So I had to use twice as much data again to illustrate some level of convergence. And now we can only really say that the first 2 modes are approaching convergence. And the first 2 modes in this case only represent 45% of the fluctuating energy, so less again. But now when we look at the modes 1 and 2, the temporal modes are again a temporal shift of each other. And now we can see in modes 1 and 2, again, obvious 2-dimensional structures. If you may remember that movie I played at the very beginning of this case, it wasn't obvious that there were any 2-dimensional structures there. But they were there, they were just hidden amongst all of the other fine-scale turbulence. Okay, so that's pretty much it. In response to the research questions I proposed initially, what are the characteristics of the uncontrolled case? There is 2D bluff body shedding and a high-frequency shear layer structures at the leading edge. And how to most efficiently represent these scales of motion is to use proper orthogonal decomposition. Okay, so these are some selected publications. The red ones are journal papers. I didn't really talk about a lot of this stuff today. And I'd like to acknowledge the Stanford Center for Turbulence Research for the use of the LES code, APAC and VPAC for the use of supercomputing facilities, financial support from the University of Melbourne and Air Force Office of Scientific Research, EGID for funding my stay in France, University of Polytechnica de Madrid for some stability work that I actually didn't present today, and also my supervisors and research colleagues. And open up to questions again. That's it.
Any questions, Tony?
Sure, just to help me visualise what's
Sure.
going on related to our experiences.
Yeah.
What is what would, for normal sort of size airfoil and
Yeah.
like that, what does say 1 second, what t equals 1 second non-dimensional correspond to? Like 1/10 for normal dimensions, 1/10 of a real second, or? Like
Well, it depends on it depends on the size of the airfoil. So, say for
5 metre or something like 3 metre,
for
jet.
yeah, okay. Let me go back to. I can tell you what the velocity is, and then maybe we can figure out what the time is.
Sorry.
The highest Reynolds number case.
Yeah.
This is really pushing the limits of computational resources that we've got.
Sure.
So we can't really go much higher than that using LES. Using RANds we can go higher, but this is about 10 meters per second, 10 kilometers an hour of a Boeing 747. So it's really not that fast at all.
Very slow, right?
Very slow. Things actually get a lot more complicated when you go faster. But having said that, it's 100 kilometres an hour for a unmanned aerial vehicle. So there are applications where this is relevant, but not quite yet for passenger aircraft because they're so much bigger. So for a passenger aircraft, if it's 10 kilometres an hour, which is about 30 metres per second, 40 metres per second, say, then it would be 1/40th of a second. Yeah, if it's 1 metre. So yeah, those non-dimensional seconds, divide them by 40 to get real seconds for a Boeing.
Okay.
But for a UAV, you divide it by 4. Yeah.
So what's it like outside of plane normally? For images or?
Well, if it's like this outside a plane, then it's you got trouble because it's just separated. So it's actually the idea of this sort of technology is to remove movable components during takeoff, for instance. So during takeoff, the air is controlled over the flow by moving the other ailerons. You guys have been in a plane, you've noticed the parts of the wing move. So that's the way that the air is currently controlled on a plane during takeoff. But if you can get this sort of technology to work, then you don't need any moving parts, so it's less weight, it's more responsive, and you can take off at steeper angles, which means you can reduce runway space, which means most of the energy is consumed during takeoff anyway. So if you can reduce the time and distance for takeoff, reduce fuel consumption. But having said that, we'll see this. I think we'll see this in wind turbines before we see it in planes, because if it doesn't work on a plane, then 500 people die. If it doesn't work on a wind turbine, then you don't get as much power. So I think we'll see this technology in that application first.
How many grid points did you go
There was 6 million, I think, 6 million. So I don't know how that compares to what you guys do, but yeah. I mean, this is actually quite modest compared to what people are doing now. People are doing billions now, but we don't have resources to do that sort of thing here. So that's why the approach I took during my PhD was not really to compete in terms of size, but in terms of ideas, because that's really the only way we can go forward.
I was reminded halfway through when you had the flow going from 2D to 3D.
Yeah.
Those images. Is it similar to the older experiments that I recall 30 years ago with 2 cylinders, one inside spinning and the outside I think is steady, and then you can generate just simple flows and then 2D flows and rolls in the other direction.
Yeah. Taylor-Couette flow. So you have one cylinder spinning inside another, and then initially it's all two-dimensional and nice, and then when you spin it faster, you get these sort of secondary structures spinning in opposite direction. Is that what you're talking about?
I think so. They used to claim that was somehow relevant to the atmosphere, perhaps, although it was idealised. But you remember Gertler instability was some character.
That's instability associated with curved surfaces.
Is this very similar, or do you relate it to some of those earlier types of studies? Or
well, some of the other work I've done does. The whole stability idea, that's more associated with these eigenmodes. So, yeah, that's just another complete topic. I mean, what I showed today was really how to summarize the information you've got using these POD modes. But the eigenmodes essentially determine how perturbation would grow in that environment. And those modes you're talking about are one type.
But the POPs, the ELFs, are a bit like the saturated, when the flow is saturated, and the eigenmodes is a bit like linear instability starting off.
Yeah.
So the eigenmodes explain the variance when you have fully developed turbulence, whereas the eigenmodes that determine when you're just late in the transition, so they're transition modes, if you like, and they're growing, whereas the
Yeah. So say this is your Reynolds number 200, so the flow is steady and nothing's happening. And this is Reynolds number 300, and it's saturated and you've got this nice sort of shedding pattern. So if you're going to plot, if we were to plot lift force on this body, we would have something nice and sinusoidal like that. So that's what Jorgen's referred to as saturated, I guess. But the transition from this state to this state, because you're starting off, maybe not lift force, maybe just if we're looking at a probe, it's like a point in space. So we're measuring velocity or something like that. So here, the fluctuating component is 0 because nothing's happening. But as we increase the Reynolds number, it'll do something like that, get larger and larger, and then it'll start to saturate. Does that make sense? So this is 0 here, and we're plotting u prime. So this is velocity, okay? And we can decompose velocity into a time averaged mean and a fluctuating part, or an unsteady part. So in this case, where the flow is steady, this bit is 0. So all we have is the mean. Is that, yeah? Okay, so now if we're plotting this part, the fluctuating part, for this case, the fluctuating part is nothing because nothing's happening. But as we increase the Reynolds number from here to here, it's not just going to immediately jump to this state. So there's a transition that happens. So it initially gets a little bit unsteady, and then more unsteady and more unsteady. And then when it gets to this flow state, this is a saturated part, and it just continues on like that. So the POD modes represent what's going on here, or EOF, or whatever. And linear stability modes represent what's going on here. So that's stability. So the stability part explains the transition, and the EOF explains the saturated state. So you need both of those. Both of those physics are important. So we need different modes to capture.
But that implies you have to know where the state ends and starts.
Yeah. Well, for this case, it's easy, right? Because one's steady, one's not. But yeah, for a case where they're both unsteady, and it gets more complicated. Yeah.
Then we calculate this lift force you mentioned that. With force.
Yeah. Yeah.
That seems like the crucial thing, is it, for a plane?
Yeah.
Why does it, and how does it change with the other two turbulent states? And I wonder if there's a simple understanding for why it drops.
Well, if I was to plot the lift force or lift coefficient versus angle, okay, so in this case, you've pretty much got no lift whatsoever because it's separated.
Why is that?
Because the flow's separated, and there's no when you calculate the force, it's
Not sticking to the surface.
yeah, the flow doesn't stick to the
It's
surface.
come off the top, that'd be no pressure, so you'd think it'd be pushing it up from the bottom. No.
You need the Venturi effect.
I don't have a great feel for these.
You know the Venturi effect. It's the Venturi effect that's determining the lift, right? So when it separates, you don't have the Venturi effect, effectively lifting it.
Why you're a theoretician and not a pilot?
I don't think I'm either at this point.
Well, anyway, this
I can't understand either way.
if this is the angle that the wing makes, and this is lift coefficient, then at 0 angle you get 0 lift because the streamlines above and below are exactly the same, and everything just balances each other out. So you get 0 lift at 0 angle of attack, assuming that the airfoil is symmetric, which we have here. So as that angle increases, you get a sort of increase in lift, and at the point of stall, it does something like that, which is this case that we've got here. So you want to avoid being anywhere near this sort of regime. So what this sort of technology does, it extends this out. So the addition of the control prevents stall, so you get more lift. Yeah.
So the 30,000 state for the uncontrolled state is stalled.
It is stalled.
Stalled.
Yeah, that's right. Yeah.
Try to go up too far
That's right.
We'll make the plane.
That's right. Yeah. So yeah, the takeoff angle is exactly that. Yeah. Yeah. So yeah, that's pretty much it. So
Any other questions?
if there's no more questions, I've got one other last thing to show you. Oh, are there any more questions? No? Okay. So this is my travel log that Jorgen mentioned. What was the view? Okay, so I used to do this every so many months while I was away, and now I've finished, I just sort of stuck them all together. So in 2006, I spent some time at Stanford learning the LES code. So this is that's a big S there. And while I was there, I went to San Fran and Alcatraz. I figured while I was in the US, why not go to Vegas? So that's the Grand Canyon on the right. And then New York for a bit. And then after that, came back to Australia. And then when I went off to Europe, did my first conference in Corfu. That's not a conference venue, it's just a street somewhere. And then in between conferences, I went to London. It took me ages to take that photo. You'll see that the leaves don't touch Big Ben anywhere. And then I went to Porto for another conference. It's a very nice city. And then back to Poitiers, it's where I lived for 15 months. It's blue, white, and red. That's a French flag, if you didn't get that. Yeah. And then Athens for Christmas holiday. And hung out with my dad's village during New Year's Eve, like these big bonfires, which was good fun. And then off to Madrid for a research stay. I noticed everybody wears sunnies over there, so took a few photos of that. And then had a break with a mate of mine. We travelled around from Rome to Barcelona. So this is following that. It's Rome, Florence, Cinque Terre, Barcelona. It was really hot that day. I was just sleeping. And Marseille. It's like south of France. It's pastis, if anyone has tried it. It's really good. And this is my last night in Poitiers, the guys I used to study with. That's the last barbecue I had with my girlfriend's family. It's rock melon prosciutto with Pinot. Give that a go, it's really good. And then andouillette, it's like an intestine sausage. So it's like intestine stuffed with intestine. It's good though. And this is when we came back to Melbourne. I figured, what's Melbourne? Apostles and coffee, right? So, and that's Perth. Get back to you folks. And that's it.